So we're right up here, and it starts talking about, or the section is, 3.0 subcooled liquids. And right out of the beginning of this page, it says define subcooled and compressed liquids as a knowledge requirement, and define subcooling. And we're going to do that. So back to our very important TS diagram, temperature versus entropy. And now I'm going to plot a temperature increase that we're very used to. Temperature goes up, hits the F point, constant temperature as it vaporizes, hits this G point, and then it could go up again. So this is temperature versus entropy. This is, I'm going to call this my atmospheric pressure line. So we know that that is 14.7 psia, and it shows what would happen if I added energy to a water down here that has got an energy that's less than this point F. When I have energy less than this point F, I'm less than a saturated liquid. The energy down here is called a subcooled. The energy of the liquid is called subcooled liquid. It's less than a saturated liquid. It's not saturated with energy yet. And if we add energy to a subcooled liquid, I see temperature go up. This is where I saw a temperature increase as I started adding energy. Temperature goes up to a subcooled liquid. So a subcooled liquid is one that exists less than the saturated liquid point. And we have a great equation for it. I know that the enthalpy in BTUs per pound mass of a subcooled liquid is going to be equal to, well, it's going to be something less than this point. So I'll use that as my starting point, and I'll subtract. And this is really neat what I'm going to subtract. I'm going to subtract the specific heat capacity of water multiplied times saturation temperature, in this case would be 212, minus actual temperature. So we could figure out the enthalpy of a subcooled liquid that way. I know it's something less than the enthalpy of the saturated vapor. If I assume the specific heat capacity of water down in that region was 1, then I just have to know the difference in temperature. So essentially, if I said I was right here, I'm finding out the difference in temperature between 2 points, and the difference in enthalpy between 2 points would give me the specific heat capacity. If I knew the specific heat capacity, and I knew the change in temperature between those 2 points, and for the atmospheric pressure line, I can look that up, I could solve for the enthalpy of a subcooled liquid. So if I said this point right here is 212 degrees Fahrenheit, I know that the temperature has to be something less than that. And the temperature subcooled is equal to, well, that's the saturation temperature, which it can saturate it with energy. So it's going to be Tsat minus the actual temperature. Such that if I was at 80 degrees, well, what is the temperature subcooled? Well, 212, I'm at 80 degrees, I have 132 degrees of subcooling. I'm 132 degrees subcooled liquid. Now, another name for that, another name for subcooled liquid is a compressed liquid, which is one of our knowledge requirements. It's either compressed or subcooled liquid. Just a liquid that exists at an energy less than saturation for those existing pressure conditions. And subcooling is the process by which it removes enough energy such that if I was right here, if I reduced enough energy such that I got to this point and then I went all the way down to here, I would have subcooled this water and steam mixture that is occurring right there. I would have subcooled it. Once I get past this point, this is all subcooling. This is a certain amount of subcooling. This would be a lot more subcooling. So this is a TS diagram. It's going to be very useful. You can see that our pan of water started here. It raised its temperature and volume up till it became saturated. Then it just started evaporating the water over until all of the water was gone out of the pan. All I had was steam here. And if I continued to add energy to a saturated vapor, I would see a temperature increase again. Temperature would go up. Now go ahead and turn the page and you'll see a TS diagram. We actually I actually see a TS diagram here on the following page, and there's a knowledge requirement there. Describe the effects of pressure on density or specific volume of a liquid. Describe the effects of pressure on density or volume of a liquid. Well, let's take a look at that on this TS diagram. We'll draw a new one. We're going to keep drawing this over and over again for understanding. We're going to apply it to a lot of different processes. Once again, TS diagram. It's temperature versus entropy. And here's this thing here. And let's go ahead and do something a little different. I've got 0.1 of a subcooled liquid at a certain pressure. I raise its energy level up till I get to this point F. And now I continue to add energy and I don't see the temperature change, right? It was just at that constant temperature right there. And then when I got here to the G point, if I added energy, I would see temperature go up again. If I said this represents the atmospheric pressure line, let's go ahead and put another pressure line in there. Pressures that exist above atmospheric pressure are going to be up here, and pressures below atmosphere will be down here in a vacuum. So here's a pressure line. I'm going to get rid of that F, put it down here for now, and get rid of this G. So this F point, this is the G point, and remember the distance between the two is called F to G, FG. So here's a new pressure line. So I could call that, just on this drawing, I'll call that the 500-pound pressure line, 500 PSIA. And then if I wanted even farther, there's the 1,000-pound pressure line, 1,000 PSIA. And that's supposed to be a constant pressure right there. So let me redraw it just a little bit. Subcooling at 1,000 PSIA. Notice that I'm constantly using absolute pressure scale. That's on purpose. We always want to think in absolute pressure scales, not gauge pressures. So we know that at 500 pounds, if I added energy to a liquid that was subcooled at 500 pounds, it would reach this F point. Nice to note that the enthalpy at the F point of water is here, and the enthalpy is actually higher up there. It's also the entropy, but we're going to deal with enthalpy so much here in a bit, but you can also see the entropy is here. The entropy is here. It's gone over a little bit because of the vapor dome, but the saturation temperature for that pressure is higher. See how the pressure and temperature relationship is kind of going up? As pressure goes up, there's a new higher corresponding saturation temperature on this side. Pretty cool. And this is all superheated vapor out here. Once I cross this line right here, I'm up into this superheated region. Once I'm over here, I'm in the subcooled region. So that's these two places here and here are where I see sensible heat additions. Because once again, as temperature goes up, if I can actually see that, that is a sensible heat addition. Across these lines, we're going to end up calling that what's known as a latent heat addition. And a latent heat addition occurs at a constant temperature. If you're following along, you'll see that we said describe the effects of pressure on density or specific volume. Well, it's pretty straightforward. A review of what we had, remember, pressure was equal to density times height divided by 144, or it was equal to height divided by specific volume times 144. So in terms of describe the effects of pressure on density or specific volume, well, if you increase the density, that essentially that's a pressurization when you're increasing the density. You're packing more mass into the same volume. Well, what if I increase the volume? Well, increase the volume would result in pressure coming down. You're allowing something to expand. It's getting less dense. Remember, density and specific volume are the inverse of one another.